Hey guys, this is Harsh Thamke.
I'm Ganesh Rai.
We are going to discuss a research paper on development of 765 kV transformer protection relay from IEEE.
And this paper was introduced by
Kentaro Kobayashi, Zayajiro Tang, Yasutaka Sonobe, and Masato Okazaki.
Let me give an introduction on it. Currently, ultra high voltage UHV systems are under development in many countries around the world. The UHV system operates at 765 kV and studies for the application of this technology began in the year 1990s in the country Korea. Development of 765 kV transmission system was completed and has been in service since 2002.
So now I'll be talking about UHV transformer and its protection scheme. So transformer capacity must be increased for application within a UHV system, and hence the size of the transformer has to be significantly increased. But when we enlarge the size of the transformer, one huge issue comes into picture, that is transportation. So when there is a problem, there's always a solution. And in order to solve this particular problem of transportation, instead of using one huge UHV transformer, it is usually considered to construct the transformer using two tanks in parallel. So the single line schematic diagram for a two tank transformer is shown in the figure. When it comes to the configuration of a two-tank transformer, it generally differs from that of the conventional single-tank arrangement, and hence it is impossible to apply the general transformer protection scheme used for extra high voltage applications. And the protection functions are implemented as main functions within the UHV transformer protection scheme.
UHV transformer protection scheme. Standard transformer protection relay is done in four methods. First, corresponding increase in number of analog inputs, configuration of the current balance relay, implementation of CT saturation countermeasure, high speed operation of differential relay. Let me tell you the first method. Increase in analog inputs. In Korea, in general, about 345 kV, the substation busbar configuration is usually a 1.5 CB arrangement. Both the 765 on the primary side and 345 kV secondary side of the power transformers are connected to a 1.5 CB busbar. The number of analog inputs is increased to 45 in total. In order to accommodate this large increase in the number of analog input, 6 bay units BU are used for the current input, and a single central unit CU is provided to serve as an arithmetic unit in which the voltage inputs are introduced for the whole system.
So now talking about current balance relay. Current balance relay is an element for detecting the unbalanced current between the tanks of two transformers in parallel. Under normal operating conditions, the current from each tank are almost equal. For any internal short circuit faults that occur, the current from each of the tank becomes unbalanced. In accordance with the basic principle of current balance relay, relay operation is achieved by detecting the difference between the current from the two tanks, which becomes the operating value or ID. It is the basic equation based upon the principle of 6-1s applied to the series winding. This is the characteristic graph of ID versus IRES.
And the third one is implementation of CT saturation countermeasure. The 765 kV busbar arrangement incorporating the primary side and secondary side of the transformer utilizes 1.5 CB busbar. The fault current flowing in the general 1.5 CV busbar system as shown in the figure. When an external fault occurs on 1.5 side of CB bar or like external to primary, the current through the bus bar and the transformer will combine. As shown in the figure, the differential current error can also cause unwanted operation of the differential relay. As a countermeasure, a waveform discriminating element WDE adapted from our bus bar protection is utilized. The second figure shows an example of a saturated CT waveform during an external fault. During one cycle of the saturated CT waveform, there are periods of saturation and non-saturations. The differential current shown is the error current resulting from CT saturation.
Now talking about the high-speed operation of this protection relay. In order to minimize the electrical and mechanical stress to equipment on this 765 kV system when fault occurs, a high-speed operation of the protection relay is desirable. In this 765 kV project, the operating system of the transformer protection differential relay must be less than 30 milliseconds. In order to respond to this requirement, the internal arithmetic algorithm has been optimized. In addition, within the transformer percentage differential relay, a second harmonic detection function that is named as the 2F block has been implemented in order to avoid unwanted operation when inrush current occurs. An outline of the 2F block configuration is as shown in the figure. The 2F block detection is used to detect the second harmonic current superimposed on the differential current. The waveform of the inrush current contains a certain level of second harmonic. About the commercialization of this particular project. This project of the transformer protection relay was commercialized in Korea in 2010. These transformer protection relays are very important as it protects against faults and overloads. It also reduces the risk of catastrophic failure to simplify eventual repair.
Thank you guys for watching the video,
And if you made it till here,
then we hope you understood the basic idea about the protection relay.
and if you have any doubts regarding this project, then let us know in the comment section below. And until then, peace.